Hi everyone, we are continuing on with microstates and Boltzmann. This is where we left off from our last video. So remember that on Friday we discussed spontaneous reactions, reversible and irreversible reactions. We also discussed how spontaneous reactions are considered to be irreversible processes. And we talked about first law of thermodynamics, meaning that energy cannot be created nor destroyed, and the mathematical statement for that was my delta E equals Q plus W, E representing that change in energy, Q representing heat, which is also just a form of energy, and work, which is represented by W, again, another form of energy. Okay, so the last thing that we left off with was Boltzmann. And Boltzmann describes entropy on more of a microscopic level. So what we've been talking about before was more on a macroscopic level and macroscopic examples. But Boltzmann really focused on something called a microstate. Now again, let's assume that we have two valves that are connected through a stopcock, and I have in one of the valves two particles, one red, one blue. And if I open the stopcock, I can have four different arrangements. And these different possibilities are going to be called microstates. Now, Boltzmann thought that as I move from A to any of these microstates, any of these possible arrangements, then I could, from A to B, have more disorder. So the more microstates that one has, the more disorder one has. Now, how can molecularly we exhibit more entropy? Well, molecules can exhibit different types of motion. So there's three different types that we're going to focus on. There's translational, vibrational, and rotational. Translational is where an entire molecule can move from one place to another. That's just translational movement. Vibrational is where we're going to have periodic motion of atoms just within the molecules themselves. So I can have vibrations as the atoms are kind of moving in the molecule. I can see that we have vibrations just from, if I'm looking here, I can have some vibrations between just the molecules moving. You can't tell it all the way that this laser pointer is moving, but ultimately just motion of atoms within the molecule, they're going to be vibrating. I can have a rotational type of motion as well, and that's just where I can think about one of the molecules and one of the atoms particularly on an axis. So let's say that we have this axis here, and then that molecule can rotate around that particular axis. When you have rotational type of motion, that rotational type of motion will always rotate around the sigma bond, okay? So just even more specific with rotational motion. Now, Boltzmann envisions that the motion of a sample of molecules at a particular instant in time, it's like taking a snapshot. So all of these microstates are happening in instants. So these microstates aren't going to last for a very long time if I'm thinking about it in the molecular level. And they can't, because think about the molecules are constantly moving. So because they're constantly moving, a microstate is really just thinking about it as a snapshot. Okay, so one more definition I think that I want to write for us for microstates is going to be that a microstate can also be thought of as a single possible arrangement for positions and for kinetic energies of molecules. Now, that's going to be our single possible arrangement. That's our snapshot. And then it's about the positions, thinking about vibrations, rotational movement, thinking about translational movement, and then also all of the energy that's associated with them. And we're going to kind of focus more on the energy in the next couple of slides. So each thermodynamic state or each thermodynamic process has some type of characteristic number of microstates that are associated with them. So if I have a lot of microstates, then we're going to have a lot of entropy. And I know that because Boltzmann found that entropy is somehow related to microstates. And he came up with this mathematical expression here. He says that S, which is entropy, is equal to K times the natural log of W. And W is going to be our variable that represents microstates. K is just a constant. So K is Boltzmann's constant, and that's given to you here. Where would you find Boltzmann's constant on your AP test? That would be on the constants page. So ultimately, if K is just a constant, then really I'm thinking about entropy and microstates as having a direct relationship. So if microstates increases, then entropy also has to increase. Okay, if we kind of rearrange some of this a little bit, we can just think about the last slide was talking about just entropy. So I'm not thinking about a change in entropy. I'm thinking about taking that snapshot. I'm thinking about what would the entropy be at that one moment in time. But guess what? We said yesterday that it's really hard to find that one moment in time in terms of entropy or in terms of enthalpy in anything. It's really hard to measure that. So instead, we have to try to find the change in entropy for a process. So when we're trying to find change in entropy, we're going to have our final microstates minus our initial microstates here. And if we do some algebra, I know that taking the natural log of the microstates final minus natural log of the microstates initial is the same thing as saying the final microstate, the natural log of the final microstates over the initial microstates. So this is the formula of what I would find the change in entropy. So this is more than likely what you will be using, because we can't find the entropy of just a snapshot in time. We're going to have to find the change in entropy for a process because it's really hard to know what's happening in between. And again, like we said, entropy will increase with the number of microstates in the system. The number of microstates also will increase, or entropy will also increase, if the following things increase. If temperature increases, then entropy increases. And we've kind of already talked about that before, and that should make logical sense to us. If I increase temperature, then I'm going to have the molecules moving. Molecules will be moving more. There will be more pressure. Ultimately, I can think about with temperature, distribution speeds, the speed of each molecule is also going to be greater. So there's more kinetic energy, and more kinetic energy can lead to more microstates because I can get more possible arrangements. I can get more snapshots in a small amount of time. Volume. If volume increases, microstates can also increase. If we increase volume, then greater volume will mean a greater number of different positions. So I can have more microstates because I can have more possible arrangements of the molecules in a specific set of volume. So if I have greater microstates, I have greater entropy. And then finally, the number of independently moving molecules themselves. If I have more molecules, then I can have more snapshots of individual molecules or pairs of molecules, and then all of those snapshots together are going to increase then the amount of microstates. So temperature, volume, and the number of molecules. If those increase, number of microstates increase, so entropy increases. Entropy is also going to increase with the freedom of motion of molecules. If we just said in the last slide that entropy increases when temperature increases, then this should make sense, because if we're starting off with a solid, they have more structure, they are more rigid, they only really vibrate in terms of their motion. But then if I move to liquid, they have more freedom of motion, they are able to rotate, they're able to vibrate. So I would have more microstates in water than I would in ice, because I have more movement, more freedom of motion here in water than liquid water than I do in ice. And then if I think about water vapor, they're even more spread out. So they have complete freedom to have vibrational movement, to have rotational motion, and to also have translational motion. They'll have the largest number of microstates. So I can say that a solid is going to have the least amount of entropy. A liquid will then have a little bit more entropy than a solid would, but a gas is going to be the best in terms of increased entropy. In a solution, generally when a solid is dissolved in a solvent, entropy is going to increase. And that's because I'm starting off with a solid and then a liquid, and at the end I'm ending up with ions, so I'm separating out that solid into its ions. So I'm increasing then more microstates, thus increasing entropy. So I'm starting off with something that's more intact, and then I'm ending with all of these ions, so entropy is going to have to increase. Some extra things just in terms of when entropy increases. So entropy increases when gases are formed from liquids and solids. Okay, well that makes sense because we just said that gases would have a higher entropy than liquids and solids would. Entropy will increase when liquids or solutions are formed from solids. Again, that makes sense. Solids have a more rigid and pattern-like structure versus liquids and solutions don't. Liquids and solutions have more entropy, so that should also make sense to us. The number of gas molecules increases, entropy will increase. We've already talked about that. And then also if the number of moles increases. So if I have more moles, then I can have the possibility of having more microstates, thus a higher entropy. Okay, so let's do some practice with predicting the sign of change in entropy. So let's predict whether the change in entropy will be positive or negative for each process. And let's also assume that this happens at a constant temperature, which means that these will be isothermal processes. Okay, so in the first one, I have liquid water and then I have water vapor. So if I'm moving from what's a liquid to now what's a gas, then I know that gases have more entropy than liquids do, so my change in entropy here will be positive because entropy is disorder, so I am moving towards disorder. So my delta S I can predict would be positive here for the first one. In the second one, I have silver ion plus chloride ion is going to react to form a solid, so I have silver chloride. Okay, so I have pieces, silver ions, silver and chlorine coming together to become more stable, more structured, having more of a pattern, a regular repeating pattern. So I have more entropy with the ions. I have less entropy as what I'm forming. So I would say this would have a negative delta S simply because I'm becoming more ordered. And entropy again is just disorder. So delta S would be negative here. And then in the third one, I have 4 moles of iron plus 3 moles of oxygen is going to yield iron 3 oxide. Actually, I want everybody to do the last two. So we've done these two, you try these two. Okay, in each pair, choose a system that has a greater entropy and explain your choice. In each pair, choose a system that has a greater entropy and explain your choice. I also want you to try this one. And what is this? This is slide 23. Okay, so first thing that we have to do on Monday is go through slide number 23 to check if you're right on the final two and then on these three. Third law of thermodynamics simply states that the entropy of a pure crystalline substance at absolute zero is going to be 0. If we decrease the thermal energy of a system by lowering the temperature, the energy stored in translational, vibrational, and rotational motions has to decrease. So let's think about this again. If I'm decreasing thermal energy, by lowering temperature, then if I'm lowering temperature, that means that all of the types of motion are going to have to decrease. As less energy is stored, the entropy of the system is going to have to also decrease. I don't have as much motion. I'm starting to become more rigid in structure, so I have less disorder, less entropy. If we keep lowering the temperature, though, we eventually could reach a state in which the motions were essentially stopped, and that would be at absolute zero. So a point where maybe we would have just one single microstate. So of course this is hypothetically speaking because we've never reached absolute zero yet. But if we did reach absolute zero, we would say that the entropy of a pure crystalline substance at absolute zero, where there's no motion at all, would be considered zero. Okay, standard entropies. In terms of a standard entropy, this is super similar to standard enthalpies that we did in chapter 5. So when we talk about a standard entropy, we usually think about a molar entropy value of a substance. Standard entropies will tend to increase with increasing molar mass, and larger and more complex molecules have greater entropies, which they should, because we just said that standard entropies tend to increase with increasing molar mass. Standard entropies are also, of gases, are also going to be greater than liquids or solids, and that's just because gases already would have a higher entropy than a liquid or a solid. So you will see that the standard enthalpy numbers over here, like if we're looking at this chart, gases will typically have higher values for S than liquids and solids will. Now, when we talk about standard anything, standard enthalpy, standard entropy, remember that we add that little degree sign up at the top, and that's just because that's indicating to us that it's a standard. So it's at a particular temperature. Just like with enthalpy change, with standard enthalpy change, entropy is going to be the exact same thing. So entropy changes for a reaction. We can find that by taking the standard change in entropy, by taking the standard entropy of the products, the sum of them, and subtracting it from subtracting the sum of the standard entropy of the reactants. These are values that are listed in the back of in an appendix in your book. It's either Appendix C or Appendix D, I'm not sure. N and M are just the coefficients in your balanced chemical reaction. So calculate the change in standard entropy of the system. And I have nitrogen, hydrogen, and this is at 298 degrees. My Promethean board just shut off, guys. I'm going to have to turn it back on. I'm sorry.